Hello and welcome to today's edition of our Tech Talk Online. My name is Herman Hoker. I've been working at Bloom Novatest for 20 years and I am currently a sales manager for measuring components for Central Europe. I'm also a product expert for our bore gauges. And it's this interesting technology that I'd like to present to you in today's Tech Talk Online. I've structured my presentation as follows. First off, I'll be taking a general look at the process of measuring workpieces on metal cutting machines. This will be followed by a second block in which I'd like to present the structure of the Bloom systems BG60 and BG61 and a few application examples. I'll use the third and final block to focus on our new control and evaluation software BG Vision. To illustrate the difference between a switching measuring system and the bore gauge, here's the schematic structure of a measuring sequence with the traditional workpiece probe. Upon contact with the workpiece, a trigger signal is emitted by the touch probe, which is then sent to the control via a receiver. The axis positions in relation to the trigger point are read out and a measuring result is determined using the Bloom measuring cycles. The corresponding measured values are stored in the control. The video demonstrates use of a probe to ensure the correct machining position in a mass production process. Experts for mass production processes are bound to feel a bit anxious after 10 to 15 seconds, at the latest, when the machine isn't producing any chips but is instead being misused as a measuring machine in the primary processing time. This video shows the measuring process after being optimized by Bloom. The measuring point and the probe ball are also flushed and freed of chips during the measuring process. The measuring process was carried out with the normal traverse and measuring speeds for Bloom TC probes, and yet, you can see that even in the optimized measuring sequence the 4-point measurement of a bore or diameter still takes over 4 seconds. If, as in this case, several workpiece measurements need to be carried out, the measuring time will increase the actual cycle time of the part considerably. The measuring time is therefore also a key criterion when it comes to using a bore gauge. BGs require only a fraction of the measuring time of the switching probe. A second criterion can be the accuracy. As we've seen, the touch trigger probe works with the axis and thus with the accuracy of a machine. In other words, despite the switching accuracies of the Bloom TC system in the 1/10 of a micrometer range, precision of the probe measurement is still limited by the machine tool. Another criterion can be the measuring point accessibility. As an example, the image shows an extended bore gauge that measures the diameter of a bearing channel. This wouldn't even be possible with an extended switching probe and a special stylus in line with the normal accuracy requirements for the task. If one or more of these criteria apply, then the bore gauge is an ideal solution. The example on the left shows the achievement of all three criteria. A pivot bearing for wheel suspension in a passenger car features a bore with H6 tolerances to accommodate the shock absorber. This hole is produced during the last machining step on a rotary indexing machine for subsequent clamping of the shock absorber. An in-process measurement was therefore necessary. Measurement using the switching probe would be too inaccurate and was not viable due to the cycle time specification of the rotary indexing machine. BG60 solution using the example of a passenger car pivot bearing. The required accuracy is easy to achieve with the BG60. With a measuring time of just 2.3 seconds, the target of 4 seconds was clearly undercut. By positioning the measuring system in the working area, it's possible to move to the measuring position very quickly. In the next block, I want to go into a bit more detail about bore gauges. I'd like to show you some more application examples of the devices and explain their structure. In this illustration, you can see the structure of the BG60. Contacting the two measuring elements and pressing them in causes a measuring needle to be forced into a wear-free optoelectronic sensor. This floating measuring mechanism ensures a high level of accuracy independent of position, even if the gauge is not centered exactly. In the following film, I'd like to show you an application using the BG60. It shows the production of a tightly tolerated diameter on a connecting rod. In the past, multiple measurements involved manual, time-consuming and labor-intensive activities. Firstly, the actual size of the diameter needed to be recorded and then the bore was reworked several times to achieve the target dimension. The BG60 solution enables a continuous process chain of measuring. The customer has been able to fully automate this process step and has so far not encountered any scrap when manufacturing these large and expensive engine parts. Those of you who are involved in mass-producing parts will no doubt find this application slow. In fact, this specific customer was not too concerned with the actual measuring time but more with the very high level of accuracy of the expensive parts. The next film illustrates yet another application. This is a preliminary investigation to determine whether it's possible to measure parts using a FANUC robot and the BG60. The BG60 is designed to deliver high-precision results even with relatively inaccurate positioning, in example even on simple machines or robots. The machine or, in this case, the robot only serves to position the BG system at the measuring point. I'd now like to present an alternative bore gauges design. It's the BG61, a system that operates with single measuring elements. Up to 8 of these single elements can be installed on the gauge. This allows you to measure, for example, 4 diameters in parallel. The BG61 can also be used to detect large bore diameters where the drive needle principle of the BG60 reaches its limits. Variants measuring 30 mm in diameter up to several hundred millimeters are possible. The schematic diagram shows the principle of the BG61. A diameter is determined by 2 facing sensors. In the application example here, you can see a BG61 applied for the fast detection of 2-step cylinder bores. The bores measuring 152 mm and 153 mm in diameter must be manufactured with a high level of precision, since the cylinder liner is pressed in directly after machining. This application example also shows that speed was not the main criterion for use of this particular bore measuring head. Rather, accuracy and accessibility of the measuring point were the decisive factors. In the application shown, we've already addressed the topic of continuous process chains several times. Here's a schematic illustration of this type of process. The goal is the automated mass production of parts with tight tolerances. In the third and final part of my presentation, I'd like to introduce the evaluation software BG Vision for bore gauges. BG Vision is a measuring and visualization program for evaluating measuring data. The program can be used to create so-called workflows, in example sequence programs for a measuring process. Further, it's also applied to log and visualize measured values and an associated statistical evaluation. The program supplies QDUS-compatible data. When used for diagnostic purposes, BG Vision provides a quick overview of the hardware components installed on the machine. In addition, the data from all the installed bore gauges is stored in the program, including the actual diameters and corresponding measuring points. Measuring characteristics can be easily created and these characteristics can be accessed multiple times. For example, a program for 4 clamped workpieces where the same feature is to be measured can be created very easily and quickly. Creating a measurement sequence is simple and intuitive using standardized measurement steps. This is achieved with the aid of a modular system of standards. On the left of the image you can see the already created workflows. On the right there's an overview of the steps of the selected workflow. If you take a closer look, you'll see a display of the measured values of the current workflow. These values are structured according to the individual steps. The display shows nominal and actual dimensions as well as tolerance and warning limits. If the user only wants the results of the measuring steps to be displayed, the positioning steps can be hidden. A statistical display can be called up for each individual measuring step. This shows the sequence of the last values and the program outputs statistical data for the measuring step. Even when there are very many features within a measuring process, BG Vision offers an exceptionally clear overall view. This provides the machine operator with a quick and accurate overview, even when dealing with very complex measuring processes. I've now reached the end of my presentation and would like to summarize what we've seen. BG technology allows fast and precise measurements. This means that it can also be used in mass production applications during the primary processing time. The user is able to achieve levels of accuracy and process at the machine that would otherwise only be available in the measuring room. What are the advantages for customers? Thanks to its high level of accuracy and machine independence, a BG can be used without restrictions as a measuring device in quality assurance processes and logging operations. This enables you to reliably control high-precision manufacturing processes. Tools can be used right up to the end of their service life, as wear or breakage is detected. If something goes wrong in the process, it's possible to intervene promptly. Processes can be initiated safely without any loss of parts. Thank you for your attention. We'd be delighted to welcome you to our next Tech Talk Online.